The most shocking part of the moon mystery isn't that no human has returned in more than 50 years. It's that every generation since Apollo was promised, the return was close only to watch deadlines retreat, billions disappear, and entire lunar programs collapse. Today, you'll uncover the real reason humanity never went back to the moon and why the next attempt could still fail before another astronaut reaches the surface. Get ready. Let's begin. On December 14th, 1972, Eugene Cernan stood at the bottom of a ladder on another world. Around him stretched the Taurus Littrow Valley, a silent plain enclosed by ancient mountains. The ground beneath his boots was covered in gray regolith, a layer of shattered rock created by billions of years of impacts. There was no wind, no moving water, nothing that could erase what he was about to leave behind. Cernan climbed the ladder of the Apollo 17 lunar module and entered the cramped ascent stage. Harrison Schmitt was already inside. The hatch was closed. The cabin was repressurized. Final preparations began. A few hours later, the ascent engine ignited. The upper section of the lunar module rose from the valley in a cloud of dust and debris. Its descent stage remained behind, surrounded by equipment, rover tracks, and the last human footprints ever made on the moon. No one watching that departure knew how long those footprints would remain the last. Apollo 17 had been an extraordinary mission. Cernan and Schmitt spent roughly 75 hours on the lunar surface. They traveled more than 35 kilometers in their lunar roving vehicle and collected about 110 kilograms of samples. Schmitt was a professional geologist. He could read the landscape in ways previous crews could not. During one excursion, he discovered orange soil containing tiny volcanic glass beads. They had been produced by explosive eruptions more than 3 billion years earlier. The moon was not merely a dead gray sphere. Its surface preserved the violent history of a world that had once been geologically active. Then the astronauts left. Between July 1969 and December 1972, the United States completed 6 successful crewed lunar landings. 12 men walked on the surface. Together, the Apollo missions returned approximately 382 kilograms of rock, soil, core samples, and breccia to Earth. Those materials transformed lunar science. Researchers used radiometric dating to determine the ages of ancient rocks. They studied isotopic compositions, impact melt deposits, volcanic basalts, and particles implanted by the solar wind. Apollo samples helped establish that the moon formed early in the history of the solar system and that its surface had been repeatedly reshaped by enormous impacts. Apollo did not simply place flags on the moon. It brought pieces of another world into laboratories where they are still producing discoveries. And then, at the moment, the program appeared to have mastered lunar exploration. Human visits stopped completely. That is the paradox. The moon did not move farther away. Its average distance remains about 384,400 kilometers. Apollo spacecraft crossed that distance in roughly 3 days. Yet more than half a century passed without another person reaching the surface. During those decades, human technology advanced at a rate the Apollo engineers could scarcely have imagined. Since November 2000, human beings have lived continuously aboard the International Space Station. Crews have operated complex life support systems, conducted thousands of experiments, repaired spacecraft during spacewalks, and maintained a permanently occupied laboratory moving around Earth at approximately 28,000 kilometers per hour. Far beyond the moon, robotic spacecraft reached places that once belonged only to science fiction. Landers touched Mars. Rovers crossed its deserts. A European probe landed on a comet. Japanese missions collected material from asteroids and returned it to Earth. NASA's OSIRIS-REx delivered samples from the asteroid Bennu. Engineers also learned how to recover orbital-class rocket boosters. Stages that would once have fallen into the ocean now descend through the atmosphere, restart their engines, and land on autonomous ships. Many are inspected, refueled, and launched again. Then came the James Webb Space Telescope. Webb operates near the Sun-Earth L2 region. Roughly 1.5 million kilometers from Earth, almost 4 times the average distance to the moon. Its segmented mirror, cryogenic instruments, multi-layer sunshield, communications systems, and precision guidance hardware work together far beyond the reach of direct human repair. Humanity can maintain a space station for decades. It can operate an infrared observatory 1.5 million kilometers away. It can land rockets vertically and send robots to asteroids. So why has no human returned to a destination reached 6 times with technology designed in the 1960s? The easiest answer is that NASA simply lost interest. It is also deeply incomplete. Large organizations do not possess a single emotion called interest. NASA does not independently decide to build a lunar program, fund it for decades, and continue flying whenever it wishes. Human spaceflight depends on presidential priorities, congressional appropriations, industrial capacity, public support, international partnerships, technical readiness, and an acceptable level of risk. Remove any one of those for long enough, and even a successful program can disappear. That creates the first mystery. Why was Apollo dismantled after it had achieved what many considered impossible? The second mystery goes deeper. The drawings were not all destroyed. Engineering reports survived. Saturn V vehicles remain in museums. Apollo hardware can still be examined in extraordinary detail. Yet possession of a blueprint is not the same as possession of a working capability. A lunar program is not one rocket or one spacecraft. It is a living industrial system. It includes factories, specialized tooling, test facilities, suppliers, inspectors, launch teams, software, materials, manufacturing knowledge, and thousands of people who understand how every piece fits together. Much of that system vanished. The third mystery may be the most surprising. Modern technology is more powerful than Apollo-era technology. Computers are smaller. Sensors are more accurate. Materials are better understood. Simulation and digital manufacturing have transformed aerospace engineering. But the modern mission is no longer a repetition of Apollo. Apollo carried out what mission planners call sorties. Short expeditions designed to land, complete specific objectives, and return before limited supplies were exhausted. Artemis is intended to begin something fundamentally different. Its long-term goal is sustained lunar presence. That means missions that can return repeatedly, remain longer, reuse infrastructure, support broader scientific work, and gradually reduce dependence on equipment carried from Earth. Apollo had to keep astronauts alive for days. A sustained architecture must manage oxygen, water, power, radiation, dust, maintenance, communications, transportation, medical emergencies, and equipment failure across much longer periods. Reaching the moon is only the opening maneuver. Surviving there and returning often enough to build something lasting is the real mission. The question, then, is no longer why another rocket has not simply flown. The real question is what died after Apollo, why modern technology could not easily revive it, and what Artemis must build again from the ground up. The answer begins not on the moon, but with an aluminum sphere weighing less than 84 kilograms a machine that once convinced America that the sky above it was no longer safe. The aluminum sphere was called Sputnik 1. It carried no bomb, it had no camera, weapon, or sophisticated scientific laboratory. Its radio transmitters produced little more than a sequence of short electronic pulses. Beep, silence. Beep, then silence again. Yet every signal crossing the atmosphere carried a message far more frightening than anything Sputnik had been designed to transmit. The Soviet Union could now place an object above the United States, and Washington could do nothing to stop it. Sputnik 1 was launched on October 4th, 1957, from a site in what is now Kazakhstan. The satellite was a polished metal sphere, roughly 58 centimeters across. It weighed approximately 83.6 kilograms and carried 4 long radio antennas extending behind it. Its transmitters broadcast near 20 and 40 megahertz. These frequencies allowed radio operators, observatories, and amateur enthusiasts around the world to detect its signal as the satellite passed overhead. Sputnik completed one orbit approximately every 96 minutes. That meant it circled Earth about 15 times per day. For Americans listening on shortwave receivers, the signal seemed to come from everywhere. It passed over cities, military installations, industrial centers, and nuclear bases. There was no territorial border in orbit. There was no wall high enough to block it. The satellite itself was harmless. The rocket that placed it there was not. Reaching orbit requires far more than simply climbing above the atmosphere. A rocket must accelerate its payload sideways until it moves fast enough to keep falling around Earth without striking the surface. Gravity still pulls the spacecraft downward, but the planet curves away beneath it at nearly the same rate. This condition is called orbital free fall. For a low Earth orbit, a spacecraft must travel at roughly 7.8 kilometers per second. Although the launch vehicle must provide additional energy to overcome atmospheric drag and gravitational losses during ascent, altitude alone is not enough. A projectile fired directly upward eventually loses speed and falls back. An orbital vehicle must gain enormous horizontal velocity. Its guidance system must continuously control thrust, orientation, structural loads, and engine timing, while propellant mass rapidly decreases. Sputnik proved that the Soviet Union had mastered enough of this process to accelerate a payload to orbital velocity. That carried an unmistakable military implication. The R-7 rocket that launched Sputnik had been developed from technology intended to deliver heavy nuclear warheads across intercontinental distances. Orbital launch and long-range missile flight are not identical, but they share essential foundations: powerful propulsion, multi-stage separation, inertial guidance, high-speed atmospheric flight, and the ability to carry a significant payload over vast distances. If a rocket could place a satellite into orbit, Americans reasoned, a related system could deliver a nuclear weapon across an ocean. The psychological shock was immediate. The United States had emerged from the Second World War convinced of its technological superiority. It had developed the first atomic weapons. Its industrial output had helped defeat two major powers. Its universities, laboratories, aircraft manufacturers, and electronics companies appeared unmatched. Sputnik shattered that confidence in a single night. This was a classic technological surprise. A rival demonstrated a capability before political leaders, intelligence agencies, and the public were emotionally prepared to accept it. The surprise was larger than the satellite. It suggested that American assessments of Soviet science, education, manufacturing, and missile development might all be dangerously wrong. Newspapers placed Sputnik on their front pages. Congressional committees launched investigations. Military leaders faced questions about missile readiness. American schools came under pressure to strengthen mathematics, physics, engineering, and foreign language education. The fear was not that Sputnik would attack anyone. The fear was that it revealed a strategic future already arriving ahead of schedule. America attempted to respond quickly, but on December 6, 1957, the first Vanguard launch vehicle carrying an American satellite rose only slightly from its launch pad before losing thrust, collapsing, and exploding on live television. The failure was humiliating. The Soviet satellite continued circling overhead, while the American answer burned at Cape Canaveral. The United States successfully launched Explorer-1 on January 31, 1958. That spacecraft detected the radiation belts surrounding Earth, producing a major scientific discovery. But politically, the race had already begun with America behind. The gap became more painful over the following years. The Soviet Union sent the first spacecraft to reach the vicinity of the Moon. It achieved the first impact on the lunar surface. Luna 3 returned the first photographs of the Moon's far side, revealing terrain no human being had ever seen. Then came the milestone that transformed the competition. On April 12, 1961, Yuri Gagarin entered the Vostok 1 spacecraft and became the first human to orbit Earth. His flight lasted approximately 108 minutes. Gagarin completed a single orbit before descending through the atmosphere. The spacecraft's automatic systems controlled most of the mission. During the final descent, he ejected from the capsule and landed separately by parachute, following the mission design used by the Soviet program. The technical details mattered less than the image. A Soviet citizen had entered orbit while the United States had not yet launched an astronaut on an orbital mission. The achievement carried enormous propaganda value. Nations across Asia, Africa, Latin America, and the Middle East were watching two political systems compete for influence. Spaceflight appeared to offer visible evidence of industrial strength, scientific education, and national organization. Every Soviet victory seemed to announce that Moscow represented the future. President John F. Kennedy needed an objective large enough to reverse that impression. A small satellite would not be enough. A short flight would not be enough. Attempting to match the Soviet Union milestone by milestone would leave the United States reacting to achievements its rival had already completed. The contest needed a new finish line. The moon provided it. Landing humans there required far more energy, more accurate navigation, more complex life support, and more powerful launch vehicles than anything either nation had yet demonstrated. The objective was distant enough to reduce the value of the Soviet Union's early lead. Most importantly, it offered an unmistakable definition of victory. Either a nation landed humans on the moon and returned them safely, or it did not. There would be no ambiguous score, no complicated comparison of satellite capabilities, and no argument over whose achievement mattered more. The entire world could watch. On May 25, 1961, just 43 days after Gagarin's flight, Kennedy addressed a joint session of Congress. He declared that the United States should commit itself to landing a man on the moon and returning him safely to Earth before the decade ended. The deadline changed everything. Apollo became a crash program, a massive national effort organized around one objective and one clock. In fiscal year 1966, NASA's budget reached more than 4% of total federal spending. The agency received access to financial and industrial resources that no peacetime exploration program has enjoyed since, at its height. Apollo involved approximately 400,000 people, thousands of companies, universities, laboratories, and government facilities contributed hardware, software, materials, testing, and research. The program stretched across the country. Rocket stages were manufactured in different states. Engines were tested on enormous stands. Guidance systems were developed by specialists in computing and inertial navigation. Spacesuits, heat shields, communications networks, tracking stations, and life support equipment were built simultaneously. A crash program compresses time by spending resources. Multiple solutions can be developed in parallel. Facilities can be constructed before every uncertainty is resolved. Large teams can work on separate subsystems at once. Expensive testing can expose failures early enough for engineers to redesign the hardware. Decisions are optimized for schedule. If the choice is between a reusable system that may take longer to perfect and an expendable system that can meet the deadline, the expendable system gains an advantage. If reducing weight matters more than long-term maintainability, components are designed for the mission rather than for decades of service. Apollo was not careless. It was intensely tested and meticulously engineered, but it was engineered under conditions in which delay carried a strategic cost. Every month mattered, because every Soviet launch might produce another humiliating first. The moon mattered as a destination, but the fear of losing mattered more. That fear created the budget, urgency, workforce, and political unity that made Apollo possible. It also created pressure to accept dangers that would be difficult to tolerate in a modern program. Fear could buy speed. It could not buy perfect safety. And inside, the lunar module was a single piece of machinery that could have left two astronauts stranded alive, conscious, and completely beyond rescue on another world. There was no rescue vehicle waiting on the moon, no runway, no helicopter, no second lander parked beyond the horizon. If the lunar module's ascent engine failed to ignite, the astronauts would remain alive for a limited time. They would still have oxygen, electrical power, cooling water, and radio contact with Earth, but they would have no way home. The command module would continue circling above them. Mission Control could study the problem. Engineers could suggest procedures. The crew could inspect switches, circuit breakers, and electrical connections. None of that could create another engine. To understand why Apollo accepted such a vulnerability, it is necessary to understand the architecture that carried the astronauts there. The journey began with Saturn V. The rocket stood approximately 111 meters tall and had a launch mass close to 3,000 metric tons. Most of that mass was propellant. Only a small fraction would eventually reach the moon. Apollo used 3 major spacecraft components. The command module carried the crew during launch and returned them through Earth's atmosphere. The service module provided propulsion, oxygen, electrical power, and thermal control during most of the mission. Together, they formed the command and service module. The third spacecraft was the lunar module. After reaching lunar orbit, 2 astronauts entered the lunar module and separated from the command and service module. The third astronaut remained behind, orbiting alone. The lunar module descended using its lower section, known as the descent stage. That stage contained the landing engine, fuel tanks, landing gear, and storage areas for surface equipment. It was never intended to leave. When the surface mission ended, only the ascent stage launched back into lunar orbit. The descent stage remained on the moon as a platform from which the upper section departed. Every phase depended on the previous one succeeding. The Saturn V first had to escape Earth's gravity well. At liftoff, its first stage used 5 F1 engines. Together, they generated approximately 7.5 million pounds of thrust. For a little more than 2.5 minutes, those engines burned refined RP1 kerosene and liquid oxygen at a combined rate exceeding 13 metric tons per second. That violence had to remain precisely controlled. A liquid-fueled rocket engine does not simply pour fuel into an open flame. Turbopumps deliver enormous quantities of propellant into a combustion chamber at high pressure. An injector distributes the fuel and oxidizer through carefully arranged openings so they mix and burn at the required rate. The F1 used a gas generator engine cycle. A small portion of its propellant was burned in a separate gas generator. The resulting hot gas drove a turbine connected to the fuel and oxidizer pumps. Those turbopumps then forced the main propellant flow into the combustion chamber. After powering the turbine, the gas generator exhaust was discharged rather than being routed into the main chamber. That distinction matters. In a staged combustion engine, the exhaust from a preburner is fed into the main combustion chamber, allowing more of the propellant's energy to contribute to thrust. This can produce greater efficiency and chamber pressure, but it also increases pressure, material demands, and operational complexity. The F1's gas generator cycle was less efficient than staged combustion, but it was comparatively direct and robust for an engine of unprecedented scale. Even so, the F1 nearly encountered a problem that could have destroyed Apollo before it began. Combustion instability occurs when pressure oscillations inside a rocket engine reinforce themselves. Instead of producing a smooth, controlled burn, the combustion process begins generating powerful acoustic waves. Those waves alter the flow of propellant through the injector. The altered flow changes the combustion rate. That change can strengthen the pressure oscillation even further. A destructive feedback loop can develop in milliseconds. At the energy levels inside an F1 chamber, severe instability could damage the injector, erode chamber walls, disrupt cooling, or destroy the engine. Engineers redesigned the injector and installed baffles that divided portions of the injector face. These structures disrupted the pressure waves before they could grow uncontrollably. During testing, engineers deliberately triggered instability using small explosive charges inside operating engines. The combustion had to recover almost immediately. If it did not, the design was not ready to fly. That was Apollo engineering at its most formidable. It did not assume failure would never begin. It forced failure to appear during testing, then demanded that the system suppress it. But not every risk could be removed by adding another component. The lunar module's ascent engine faced an entirely different requirement. It did not need immense thrust. It needed absolute simplicity at the moment of ignition. The engine used hypergolic propellants. Its fuel and oxidizer ignited spontaneously when they contacted one another. No spark plug, pyrotechnic igniter, or complex ignition sequence was required. Opening the correct valves allowed the propellants to enter the chamber and begin burning. This chemistry was toxic and corrosive, but it offered a crucial advantage. After sitting in the lunar environment, the engine could start without relying on a separate ignition device that might fail. The ascent engine also used a pressure-fed system. Helium pushed the propellants from their tanks into the combustion chamber. This eliminated turbopumps and the high-speed rotating machinery they would have required. Fewer moving parts meant fewer possible failure points. The engine was intentionally simple because its job was unforgiving. Once ignited, it lifted the ascent stage from the surface and placed it on a trajectory that allowed rendezvous with the command module. Yet there was no independent backup ascent engine. A second complete propulsion system would have added tanks, plumbing, valves, structure, and mass. Every additional kilogram placed on the ascent stage required more propellant for landing and takeoff. That demand propagated through the architecture, increasing the mass that Saturn V had to launch from Earth. This is known as the rocket equation's compounding effect, even without expressing it mathematically. Extra mass at the Moon requires additional propellant. That propellant requires larger tanks. Those tanks add more mass, which requires still more propellant. Redundancy was therefore not free. Apollo protected critical functions where practical, but the architecture still contained single points of failure. The seriousness of that reality appeared before Apollo 11 launched. Speechwriter William Safire prepared a statement for President Richard Nixon titled, "In Event of Moon Disaster." It was intended for use if Neil Armstrong and Buzz Aldrin became stranded on the lunar surface. The document was not a prediction. It assigned no reliable probability to disaster. It was evidence that the possibility was real enough to require preparation at the highest level of government. Apollo 13 later demonstrated how quickly an apparently isolated malfunction could spread across a spacecraft. An oxygen tank in the service module failed during the flight to the Moon. The loss was not limited to breathing oxygen. Apollo's fuel cells combined hydrogen and oxygen to generate electricity, producing water as a byproduct. As oxygen was lost, electrical generation collapsed. Water became limited. Thermal control deteriorated. Navigation, communications, and life support all came under pressure. One failure produced a cascading failure because several essential functions depended on the same resource. The lunar module, designed to support 2 astronauts for a brief surface mission, became a lifeboat for 3 men. That survival revealed the difference between redundancy and resilience. Redundancy means providing additional components or pathways. Fault tolerance means allowing a system to continue operating after something fails. Resilience goes further. It includes the ability to reconfigure equipment for purposes its designers did not originally intend. Apollo 13 survived because hardware, procedures, engineers, and astronauts formed a system capable of adaptation. But redundancy can also hide a dangerous weakness. If 2 backup systems depend on the same power supply, cooling loop, software logic, or manufacturing defect, one event can disable both. This is a common mode failure. 2 components may appear independent while sharing the same underlying vulnerability. Apollo was not recklessly built. It contained extraordinary engineering, aggressive testing, and carefully chosen redundancy, but it belonged to an era with a different tolerance for danger. Political leaders feared losing the space race. engineers faced a deadline tied to national prestige. Astronauts accepted that some mission phases offered no rescue and no complete backup. The program accepted those dangers to reach its objective before time ran out, and when that objective was finally achieved, Congress began dismantling the machine before its last flight had even left Earth. Apollo did not end because America ran out of rockets. Saturn V hardware already existed. Lunar modules were moving through production. Astronauts were training. Scientists were evaluating landing sites that could answer questions left unresolved by the first missions. Yet Apollo 18, Apollo 19, and Apollo 20 never left Earth. Their disappearance was not caused by one dramatic decision. There was no single meeting where an official declared that the moon no longer mattered. The program was reduced in stages. Each cancellation appeared defensible when viewed alone. Together, they closed the lunar frontier for more than half a century. The first major cut came before Apollo 11 had even landed. NASA's original planning had included more missions than the sequence ultimately flown. Budgets were already tightening during the late 1960s. The agency had built the factories and workforce needed for rapid Apollo production. But maintaining that industrial machine required enormous annual spending. In January 1970, NASA announced the cancellation of Apollo 20. One of the remaining Saturn V launch vehicles was reassigned to launch Skylab, America's first space station. The decision did not mean lunar science had been judged worthless. It reflected competition inside NASA's own human spaceflight program. A Saturn V could launch another crew toward the moon, or it could place an orbital laboratory weighing roughly 77 metric tons into low Earth orbit. It could not do both. Later in 1970, financial pressure deepened. Apollo 18 and Apollo 19 were also removed from the schedule. The remaining missions were rearranged, and Apollo 17 became the final planned lunar landing. The cuts were not simply a reaction to one bad budget year. Four powerful forces were pulling Apollo toward its end. The first was geopolitical success. Apollo had been created to defeat the Soviet Union in a highly visible contest. On July 20th, 1969, Neil Armstrong and Buzz Aldrin landed in the Sea of Tranquility. Hundreds of millions of people watched the event through television broadcasts and international media coverage. The result was unambiguous. The United States had placed humans on the moon first. It had demonstrated high-energy propulsion, precision navigation, digital guidance, global communications, life support, and deep space mission control on a scale no other country could match. The political objective had been achieved. The second force was the collapse of the direct Soviet challenge. The Soviet Union had developed the N-1, an enormous rocket intended to support its crewed lunar effort, but all four N-1 test launches failed between 1969 and 1972. The vehicle never reached orbit. Without a credible Soviet landing approaching, another American mission could no longer prevent a strategic defeat that appeared imminent. The race had lost its opponent. The third force was declining symbolic return. Apollo 12 was scientifically and technically important. It demonstrated a precision landing near the Surveyor 3 spacecraft and returned valuable samples from Oceanus Procellarum. But politically, it could never repeat the shock of Apollo 11. The first landing changed history. The second confirmed that the first had not been an accident. Every mission after that added knowledge, capability, and experience. Yet each produced less additional prestige than the first. Economists might describe this as diminishing marginal political value. Apollo 11 delivered the central symbolic victory. Apollo 12 delivered less new geopolitical value. Apollo 15, 16, and 17 became increasingly capable scientific expeditions. But they could not make America first a second time. The fourth force came from Earth. The Vietnam War consumed lives, political attention, and federal resources. Inflation increased, urban development, healthcare, education, environmental protection, transportation, and anti-poverty programs competed for funding. NASA's budget could no longer be treated as though it existed outside the rest of the federal government. At its peak, the agency had received more than 4% of federal spending. By the mid-1970s, its share had fallen to roughly 1%. Apollo had been affordable only because the United States had temporarily decided that winning the space race justified extraordinary expenditure. Once that urgency disappeared, the same spending level became politically impossible to defend. It is tempting to summarize this by saying the American public became bored with the moon. That explanation is too simple. Public interest is not the same as television ratings. Television ratings are not the same as congressional appropriations. Congressional appropriations are not the same as strategic priority. Some Americans continued to support Apollo strongly. Scientists wanted additional missions. Aerospace communities depended on the program. Millions still followed the flights. At the same time, live coverage of later missions did not produce the universal attention surrounding Apollo 11. Networks reduced portions of their coverage. Lunar exploration became less novel as mission after mission succeeded. That did not mean the country unanimously rejected spaceflight. It meant Apollo could no longer command enough political priority to protect its budget from every competing demand. The scientific cost of cancellation was substantial. The 6 successful landings explored geographically limited regions, all on the moon's near side and mostly at low or moderate latitudes. Mission planners selected sites using a combination of scientific value, lighting conditions, communications, terrain safety, and the performance limits of Apollo hardware. Those decisions were rational. They also created sampling bias. Apollo returned an extraordinary collection of material, but 382 kilograms of samples from 6 landing areas cannot represent an entire world with a surface area of nearly 38 million square kilometers. The moon's crust is not chemically or geologically uniform. The dark lunar maria consist largely of basalt, formed by ancient volcanic eruptions. The brighter highlands contain older, anorthosite, rich crust. Large impact basins excavated material from different depths, volcanic provinces, young craters, basin rings, and regions rich in heat-producing elements preserve different chapters of lunar history. A sample collected in one province cannot automatically describe another. Rock age also matters. Apollo samples helped scientists investigate the idea that the inner solar system experienced a period of intense bombardment early in its history, but reconstructing the exact timing and duration of that bombardment requires samples tied to known geological units from multiple locations. Limited geography means limited calibration. Potential destinations for later Apollo planning included geologically distinctive regions, such as the Marius Hills volcanic province, the crater Copernicus, and other sites that might have exposed material from different depths or periods. The exact assignments changed as missions were studied and canceled. Not every proposed location had become a final operational target, but the scientific ambition was clear. Later missions would not have been simple repetitions. They could have tested whether discoveries from earlier sites applied across broader portions of the moon. Entire environments remained beyond human reach. No astronaut visited the lunar far side. Direct radio communication with Earth is blocked there by the moon itself. So a crewed landing would have required relay infrastructure and a more complex mission architecture. No Apollo crew explored the polar regions. The permanently shadowed craters that later became central to the search for water ice were not destinations for the Apollo landing program. The canceled missions therefore represented more than missing flags or photographs. They represented geological questions left unanswered for generations. Yet science alone could not recreate the political force that had built Apollo. By the time Apollo 17 departed, the program had not suffered a technical defeat. Its final mission was arguably its most scientifically productive. The spacecraft worked. The crew returned safely. The samples entered laboratories. Apollo stopped because it had completed the mission the political system had actually assigned to it. That mission was not to establish permanent lunar exploration. It was to reach the moon before the Soviet Union. Once that outcome had been secured, continued flights became increasingly difficult to justify at Apollo's cost. Some unused hardware survived. Saturn V vehicles and stages can still be seen in museums. Visitors can walk beneath them and understand their extraordinary scale. But those rockets are only the visible remains. The larger loss cannot be suspended from a museum ceiling. A rocket can be preserved inside a hangar. The workforce, tooling, production methods, supplier networks, and thousands of decisions stored in human memory cannot be preserved the same way. NASA did not forget the laws of physics. The Saturn V blueprints were not secretly burned. The equations governing orbital flight did not vanish. Engineering reports, test results, photographs, manufacturing records, and mission data survived in archives across the United States. What disappeared was something much larger. Apollo had been a living system of people, factories, suppliers, machines, and skills that could never be captured completely on paper. That distinction destroys one of the most persistent myths about the moon program. The claim usually sounds simple. NASA lost the technology required to return to the moon. But technology is not a box of drawings waiting to be reopened. A genuine technological capability has at least 4 layers. The first is design. This includes dimensions, materials, tolerances, electrical diagrams, software logic, propulsion requirements, structural limits, and the relationships between subsystems. The second layer is production infrastructure. Factories need specialized welding machines, forming dies, assembly jigs, test stands, calibration equipment, clean rooms, lifting systems, and inspection tools. Many exist only to manufacture one particular component. The third layer is the supply chain. A rocket company does not manufacture every transistor, seal, valve, bearing, fastener, chemical, wire, and sensor itself. Thousands of suppliers contribute materials and components. Some firms depend on smaller subcontractors that may be almost invisible to the organization managing the complete vehicle. The fourth layer is tacit knowledge. This is the knowledge held by people rather than documents. A technician may recognize an abnormal weld from its color or surface texture. A machinist may know that a particular alloy behaves differently after a humid night. An inspector may hear a change in the sound of a pump before an instrument records a measurable problem. These observations can be documented, but they are rarely captured in full. Experience creates patterns that are difficult to convert into formal instructions. During Apollo, engineers and technicians accumulated that knowledge through repeated production and testing. They saw components fail. They watched materials deform. They learned which tolerances mattered most and which measurements could appear acceptable while hiding a dangerous defect. Some manufacturing instructions referred to standard shop practice. That phrase made sense when the same workers had been performing the process for years. They shared an understanding of the tools, materials, and sequence of operations. Decades later, the phrase could become almost meaningless. The shop was gone. The standard had disappeared with it. When Saturn V production ended, its industrial network did not remain frozen in place. Assembly lines closed. Workers moved to the space shuttle, military programs, commercial aviation, or entirely different industries. Others retired. Specialized machines were reassigned, dismantled, sold, or scrapped. Jigs held large structures in exact alignment during assembly. Fixtures positioned components for drilling, welding, or inspection. Forming dies shaped metal into geometries that could not be reproduced reliably by hand. These were not accessories to the blueprint. They were part of the manufacturing process, encoded in physical form. Large Saturn V structures also demanded specialized welding and inspection. Propellant tanks had to remain lightweight while containing cryogenic liquids under pressure and surviving severe launch loads. A weld could appear acceptable at the surface while containing internal porosity. Incomplete fusion or microscopic cracking, radiographic inspection, ultrasonic testing, proof pressure, and destructive testing of representative samples helped verify manufacturing quality. The process depended on calibrated equipment and trained interpretation. Preserving a drawing of the tank did not preserve the industrial system capable of producing it. Apollo also required configuration management on an enormous scale. A spacecraft design is never a single, final document. Components change during development. A valve is redesigned, a wire route moves, a material specification is updated, a test reveals vibration at an unexpected frequency. A modification solves one problem, but changes the thermal or structural behavior of another subsystem. Every approved alteration creates a new configuration. Engineers must know exactly which version of each component is installed on each vehicle. Test procedures must match that configuration. Maintenance instructions must reflect the same changes. Interfaces between subsystems must remain compatible. A drawing can be authentic and still be wrong for a particular vehicle if it represents an earlier revision. Apollo documentation therefore consisted of far more than general blueprints. It included change orders, inspection records, manufacturing deviations, test reports, supplier certifications, software versions, and mission-specific modifications. Reconstructing the complete configuration from millions of records would be an engineering program in itself. Then there is material obsolescence. Some Apollo-era alloys, coatings, adhesives, insulation products, lubricants, and electronic components are no longer manufactured. A supplier may have closed decades ago. The original production equipment may no longer exist. Environmental and occupational safety standards may prohibit substances once used routinely. Replacing an obsolete material is not a simple administrative change. A new adhesive may release gases differently in vacuum. A modern insulation material may respond differently to vibration or cryogenic temperatures. A replacement alloy may have better strength, but different fatigue behavior, thermal expansion, or weldability. Each substitution can trigger new analysis and testing. Electronic systems present an even greater discontinuity. Apollo guidance computers used components built for a radically different industrial era. Reproducing those exact electronics would offer little practical value. Modern processors are more powerful, compact, and efficient. But replacing the computers changes software, interfaces, power requirements, electromagnetic compatibility, thermal management, and fault behavior. Modernizing one subsystem can force redesigns across many others. This is technology obsolescence. The original components and processes no longer fit the present industrial environment. Supply chain discontinuity creates a related problem. Even if a prime contractor survives, lower-tier suppliers may not. The company that produced one specialized seal may have depended on a chemical from another manufacturer and tooling from a third. If one hidden link disappears, the component must be redesigned, requalified, or sourced from an entirely new process. Could engineers reverse engineer the surviving Saturn V vehicles? They could learn an enormous amount from them. Modern imaging, material analysis, computed tomography, laser scanning, and non-destructive inspection could reconstruct geometries and reveal manufacturing details. But museum hardware is not a production master. Materials age, polymers become brittle, metals corrode or accumulate microscopic damage, sealants dry out, wiring insulation degrades. Components may have been modified for display, exposed to uncontrolled environments, or separated from their original documentation. A museum rocket proves what was built. It does not automatically explain every condition required to build another one safely. Even a perfect physical copy could not simply carry astronauts. The recreated vehicle would need qualification. Structures would undergo load testing. Engines would require repeated firing. Avionics would face vibration, radiation, electromagnetic, and thermal vacuum testing. Manufacturing processes would need validation. Human rating would require evidence that catastrophic hazards had been identified, controlled, and verified under modern safety standards. At that point, the program would no longer be cheaply copying an old rocket. It would be developing and certifying a new production system for an old design. That creates the central paradox. Reproducing Saturn V exactly could cost more than designing a vehicle around modern materials, electronics, factories, and mission requirements. But a modern vehicle does not inherit Apollo's flight history. It must pass through development, integrated testing, failure investigation, certification, and operational learning of its own. There is no shortcut hidden inside a museum. Apollo capability was never stored on a shelf. It existed inside an ecosystem assembled for a specific historical mission and then deliberately dismantled when that mission ended. And even if the entire Apollo machine could be restored exactly as it was, it would still keep only a small crew alive for a few days. The real challenge begins after the point when every Apollo astronaut had already left. On Earth, a broken water processor is an inconvenience. On the Moon, the same failure could become a drinking water crisis, a sanitation crisis, a thermal control problem, and eventually an oxygen emergency. The systems are connected. That is what makes a lunar outpost fundamentally different from an Apollo mission. Apollo used a largely open-loop life support architecture. Nearly everything the astronauts needed was loaded before launch. Oxygen, water, food, chemical absorbents, batteries, and other consumable materials were carried from Earth in quantities calculated for a mission lasting days. The crews consumed those supplies and returned before they ran out. Cabin oxygen came from storage tanks. Carbon dioxide exhaled by the astronauts was removed using lithium hydroxide canisters. Cabin air passed through these containers, where the lithium hydroxide chemically reacted with carbon dioxide and trapped it. The reaction was effective. It was also essentially irreversible during the mission. Once a canister approached its absorption capacity, it had to be replaced. Apollo could carry enough canisters because the missions were short. The spacecraft did not need to regenerate the chemical or recover the captured carbon dioxide. Most wastewater did not return to the life support cycle either. Some water was produced by the fuel cells as they generated electricity. But urine and other waste streams were not purified into drinking water on the scale required for the long-duration habitation. That approach becomes impossible for a base operating for weeks or months. Every kilogram launched toward the Moon requires propellant, tank capacity, structural support, ground processing, and launch performance. Water is especially expensive because people need it continuously. It is used for drinking, preparing food, hygiene, medical care, cooling equipment, and producing oxygen. A permanent or repeatedly occupied outpost therefore needs a regenerative environmental control and life support system. Instead of treating air and water as supplies that move in one direction from storage to consumption, to waste a regenerative system repeatedly collects, cleans, and returns them to use. The International Space Station provides the most mature operational example. Moisture enters the station's atmosphere whenever astronauts breathe or sweat. Water also evaporates from food, cleaning processes, and wet equipment. Condensing heat exchangers cool cabin air below its dew point. Water vapor condenses onto controlled surfaces and is collected rather than allowed to accumulate inside the station. Urine enters a separate processing stream. Recovering water from urine is difficult because the liquid contains salts, organic compounds, and substances that can foul equipment. As water is removed, the remaining fluid becomes increasingly concentrated. Minerals can precipitate. Deposits can obstruct lines or damage moving components. The station's urine processor assembly uses distillation under reduced pressure. Lower pressure allows separation at lower temperatures, reducing the energy required and limiting some forms of chemical degradation. Because ordinary gravity-driven settling does not work reliably in orbit, the system uses rotating hardware to help separate liquid from vapor. the recovered vapor, is condensed into water. It is not immediately ready to drink. Water from urine processing, cabin humidity, and other sources enters the water processor assembly. Filters remove particles and selected chemical contaminants. Ion exchange materials capture dissolved compounds. A high-temperature catalytic reactor oxidizes low molecular weight organic contaminants that remain after filtration. Sensors then monitor water quality. If the water does not meet required standards, it can be redirected for additional processing rather than sent directly to the crew. Recent improvements, including the brine processor assembly, have pushed the station's overall water recovery rate close to 98%. The brine processor addresses the concentrated liquid left after conventional urine processing. It uses membrane-based technology and controlled evaporation to extract additional water from material that would otherwise remain waste. A 98% recovery rate is an extraordinary engineering achievement. It is not a perfectly closed loop. If a system recovers 98% of a resource during each operational interval, the missing fraction still accumulates. Water leaves the cycle through leakage, discarded filters, residual waste, airlock operations, maintenance, and material that cannot be economically recovered. Over days, those losses may appear small. Over months, they become resupply requirements. The machinery also consumes resources of its own. Filters reach capacity. Catalyst performance degrades. Seals wear. Pumps develop friction or vibration. Tubes accumulate deposits. Sensors drift away from their calibration. Even a regenerative life support system must be fed with spare parts, chemicals, electrical power, and human labor. Water is also tied directly to breathable oxygen. An oxygen generation system can use electrolysis to split purified water. Oxygen enters the cabin atmosphere. Hydrogen must be stored, vented, or sent into another chemical process. On the International Space Station, hydrogen can react with carbon dioxide in a Sabatier system. The reaction produces water and methane. The recovered water returns to the life support loop, while methane is typically treated as waste. This partially closes both the oxygen and water cycles. It does not fully recycle every atom. A future lunar outpost may use similar processes, but the design cannot simply be copied without modification. The Moon has approximately 1/6 of Earth's surface gravity. That is more gravity than exists in orbit, but far less than terrestrial equipment normally experiences. Fluid management hardware must operate in this reduced gravity environment. Liquids may settle more slowly. Gas bubbles may remain trapped in pumps or tubing. Two-phase flows containing both liquid and vapor can behave differently from expectations based on Earth testing. A bubble entering a pump can cause cavitation, loss of pressure, overheating, or interrupted flow. A separator that fails to remove gas from water may send unstable mixtures into downstream equipment. The outpost must therefore control phase separation, fluid positioning, pressure, temperature, and microbial growth at the same time. Mass balance governs everything. Every person consumes oxygen, water, food, and hygiene materials. Every process produces carbon dioxide, humidity, heat, urine, solid waste, and trace contaminants. The system must track where each resource enters, how it is transformed, what fraction is recovered, and what fraction is permanently lost. A small leak is not merely a maintenance issue, it is a countdown. For a crew of 4, daily water demand can vary enormously depending on hygiene rules and recycling efficiency. Even strict conservation creates a substantial requirement over several months. Food remains even more difficult because complete food production on the Moon is far beyond the capability of an early outpost. Stored food must also remain safe while exposed to time, radiation, temperature changes, and limited refrigeration. Reliability must be designed as a sequence of defenses. The primary system handles normal operations. A backup system takes over if the primary fails. A degraded operating mode reduces consumption and preserves essential functions. Hygiene may be restricted. Scientific work may stop. Exercise schedules may change to conserve power or water. Isolation valves allow a leaking or contaminated section to be separated from the rest of the network. Emergency reserves provide time for diagnosis and repair. But two systems are not automatically safe because there are two of them. If both use the same defective seal, software, coolant loop, power bus, or contaminated water source, a single event can disable both. That is a common mode failure. True resilience requires diversity, physical separation, repair access, diagnostic tools, and crew members trained to work under pressure. A lunar base cannot be designed around the belief that perfect machinery will never break. Every machine breaks eventually. Survival engineering begins with that fact. It gives the crew enough information, spare capacity, and time to repair the failure before the failure becomes irreversible. Air can be recycled. Water can be recovered, but no machine on the moon can switch off the atomic particles already passing through the crew's bodies. Cosmic radiation cannot usually be seen, heard, or felt. It does not arrive as a glowing wall moving across the lunar horizon. Yet some extremely energetic atomic nuclei carry macroscopic amounts of kinetic energy concentrated into a particle far smaller than a human cell. By the time the crew notices the biological consequences, the original particle is already gone. Earth hides the severity of this environment. Its atmosphere places a massive column of gas between the surface and space. Incoming high-energy particles collide with atmospheric atoms, producing cascades of secondary particles, while much of the original energy is absorbed high above the ground. Earth's global magnetic field provides another layer of protection. The magnetosphere does not block all radiation, but it alters the trajectories of many charged particles. Depending on their energy, charge, and direction, particles may be deflected, trapped in radiation belts, or guided toward the polar atmosphere. The moon has neither a thick atmosphere nor a strong global magnetosphere. Its exosphere is so tenuous that individual molecules can travel long distances before colliding. Localized crustal magnetic anomalies exist, but they do not form a planetary shield comparable to Earth's magnetic field. Two major radiation environments dominate the problem. The first consists of solar energetic particles. These events are associated with solar eruptions, including powerful flares and coronal mass ejections. Shock waves and magnetic disturbances can accelerate protons and heavier ions to high energies. Intensity may rise rapidly. Depending on the event and the magnetic connection between the eruption and the moon, a relatively quiet radiation environment can become dangerous within hours or less. Solar particle events are episodic. They are not present at maximum intensity all the time. That makes forecasting and warning systems extremely valuable. The second environment consists of galactic cosmic rays. These particles originate beyond the solar system. Many are believed to be accelerated by extreme astrophysical processes, including supernova remnants. They arrive continuously from many directions. Most galactic cosmic rays are protons. A smaller fraction consists of helium nuclei, also known as alpha particles. A much smaller, but biologically important fraction contains heavier atomic nuclei traveling at extremely high velocities. These are often described as high-charge and high-energy particles. Their rarity does not make them harmless. A heavy nucleus can deposit energy densely along a narrow track through tissue. It may pass through several cells, leaving a chain of molecular damage that differs from the more dispersed damage caused by many forms of radiation encountered on Earth. The basic mechanism is ionization. When a charged particle passes near an atom or molecule, it can transfer enough energy to remove electrons. The resulting ions and excited molecules become chemically reactive inside human tissue. Radiation can damage DNA directly by disrupting molecular bonds. It can also act indirectly. Most human tissue contains water. Radiation interacting with water can create reactive oxygen species, including radicals capable of attacking proteins, membranes, and DNA. Cells possess repair mechanisms, but repair is not perfect. A single damaged DNA strand may be restored accurately. Closely spaced breaks, clustered lesions, or damage involving both strands can be far more difficult to repair. Incorrect repair can lead to cell death, mutation, or long-term changes that increase cancer risk. High linear energy transfer radiation is especially concerning because it deposits large amounts of energy over a short path. Instead of producing isolated molecular injuries, it can create dense clusters of damage. Several repair pathways may be required in the same microscopic region at the same time. Radiation protection is therefore not as simple as placing a thin metal wall around the habitat. When an energetic cosmic ray nucleus strikes aluminum, it may collide with an atomic nucleus in the shielding. That collision can fragment the original particle and the target nucleus. The result may include protons, neutrons, lighter nuclear fragments, and other secondary radiation. This is called a particle shower. The shielding changes the radiation field, but does not always remove it. In some configurations, adding a small amount of dense material can reduce one component while producing secondary particles with different penetration and biological characteristics. Regolith can behave in a similar way. A thick layer can provide substantial protection by forcing particles through more material, but interactions within that material still generate neutrons and nuclear fragments that the habitat design must consider. Shielding performance depends on composition, thickness, geometry, and the energy spectrum of incoming radiation. Hydrogen-rich materials can be valuable. Hydrogen nuclei are lightweight. Collisions with them can transfer a significant fraction of a neutron's energy without producing the same heavy fragmentation associated with some high atomic number materials. Water and polyethylene therefore offer useful shielding properties in certain configurations. A habitat can turn necessary supplies into protection. Water tanks, food packages, hygiene materials, and waste containers can be arranged around sleeping areas or a dedicated storm shelter. Instead of carrying shielding that serves no other purpose, the architecture can place existing mass where it reduces crew exposure. A storm shelter would likely occupy an internal region of the habitat. The crew would enter when monitoring systems detected a major solar particle event. Water, provisions, equipment, and additional shielding would surround the small protected volume. Space weather observatories would monitor the sun. Particle detectors near the habitat would measure changing conditions. Operational procedures would determine when surface activity must stop and how quickly astronauts must reach shelter. Radiation exposure also requires dosimetry. An active dosimeter measures radiation in real time. It can warn the crew when dose rates rise and record how exposure changes during surface excursions. A passive dosimeter accumulates a signal over time and is analyzed later. It provides an independent record that does not depend on continuous electrical power, but a detector worn on the chest does not reveal the exact dose delivered to every organ. The body itself changes the radiation field. Tissue absorbs, scatters, and produces secondary particles. Bone marrow, the lens of the eye, the central nervous system, and other organs differ in sensitivity and geometry. Organ dose must therefore be estimated using personal measurements, computational models, phantom experiments, and knowledge of the surrounding shielding. Radiation will also interact with another major unknown partial gravity. The Moon's surface gravity is about 1/6 of Earth's. Human beings have spent months in microgravity aboard space stations, but no person has lived for an extended period in lunar gravity. No confirmed long-duration human dataset shows whether 1/6 gravity is sufficient to prevent severe bone demineralization, muscle atrophy, cardiovascular deconditioning, or fluid redistribution. It may reduce some effects compared with microgravity. How much remains unknown. A lunar outpost would become the first laboratory capable of measuring the combined influence of partial gravity, radiation, isolation, dust exposure, restricted diet, and demanding surface work over long periods. The obvious solution to radiation is more shielding. But shielding requires mass. Launching mass from Earth is one of the most difficult and expensive parts of the entire architecture. The solution may already lie beneath the astronaut's boots, yet the same lunar material that could shield a habitat is abrasive, electrostatically charged, and capable of wearing through suit joints, damaging seals, and entering human lungs. On Earth, wind moves sand across deserts, rivers carry sediment toward the sea, water, weather, and repeated collisions slowly grind sharp fragments into smoother grains. Nothing like that happens on the Moon. There is no rain, no flowing water, no dense atmosphere carrying particles across the landscape. A fragment of lunar rock can retain its sharp, irregular edges for millions of years. That is why lunar regolith is not ordinary dust. It is the product of relentless destruction without the erosion that normally softens material on Earth. For billions of years, asteroids, meteoroids, and micrometeoroids have struck the lunar surface. Large impacts excavated enormous basins. Smaller objects shattered rocks and opened craters. Microscopic particles arrived at extreme velocities, repeatedly pulverizing the upper surface. Because the Moon lacks a thick atmosphere, even tiny incoming objects can reach the ground without burning up completely. Each collision transfers energy into the target material. Rock fractures, particles melt, some material vaporizes. Debris is thrown upward and falls back across the surrounding terrain. This continuous process is called impact gardening. It gradually overturns and mixes the lunar surface. Material from one depth is excavated and scattered over younger deposits. New impacts bury older grains beneath ejecta. Later collisions expose and redistribute them again. The result is not a neatly layered soil like that found on Earth. It is a complex mixture of mineral fragments, broken bedrock, impact melt, glass, and material delivered from distant locations. Among its most distinctive components are agglutinates. When micrometeoroids strike, localized temperatures can become high enough to melt small portions of regolith. The molten material cools rapidly in vacuum and binds nearby mineral fragments together. These irregular particles often contain impact-generated glass and tiny droplets of metallic iron. Agglutinates help give mature lunar soil its unusual optical and magnetic properties. They also produce surfaces that can be chemically reactive when freshly fractured. The particle sizes vary enormously. Some fragments are coarse enough to see easily. Others are finer than ordinary terrestrial dust. The smallest particles can reach deep into mechanical gaps or remain suspended inside a pressurized cabin after being disturbed. Their shapes are often angular. Their edges have not been rounded by rivers or weather. Their surfaces may contain microscopic fractures, glassy projections, and high-energy chemical sites created during impact. This produces a large active surface area relative to particle mass. The vacuum environment adds another complication. Solar ultraviolet radiation knocks electrons away from exposed surfaces. The solar wind delivers protons and electrons. Plasma conditions change as the surface moves from sunlight into shadow. As a result, lunar grains can acquire electrical charge. The exact charging behavior depends on illumination, location, particle size, local plasma conditions, and nearby equipment. But the practical consequence is clear. Dust does not simply fall away. Electrostatic adhesion helps it cling to spacesuits, tools, cables, windows, thermal control surfaces, and exposed machinery. Once attached, the dust becomes both contamination and abrasive. A radiator works by emitting heat into space. If dust changes its optical and thermal properties, it may reject heat less efficiently. Equipment designed to remain within a narrow temperature range can begin operating too warm. Dust on solar arrays can reduce the amount of light reaching photovoltaic cells. dust on lenses and navigation cameras, lowers contrast and degrades image quality. On reflective surfaces, it changes how radiation is absorbed and emitted. Inside moving hardware, the danger becomes mechanical. Particles can enter joints, bearings, hinges, and seals. As components move, the grains scrape between contact surfaces. Repeated motion increases wear, raises friction, and damages protective coatings. A seal does not need to split visibly to become dangerous. A single particle caught along its sealing surface can create a microscopic leak path. In a pressurized habitat or spacesuit, even a slow leak can gradually consume oxygen reserves. Apollo crews encountered these problems during missions lasting only a few days. Astronauts reported that dust covered their spacesuits after surface excursions. It worked into fabric layers and joints. Suit mobility became worse as operations continued. Helmet visors were scratched. Thermal control surfaces and equipment became coated. Tools and sample containers carried dust back into the lunar module. Inside the cabin, the particles no longer remained pressed to the ground by lunar gravity. Movement and ventilation disturbed them. Dust entered the breathing environment. After Apollo 17, geologist Harrison Schmitt described nasal congestion and irritation after exposure. He compared the reaction to hay fever. Other astronauts reported the distinctive odor of lunar dust after contaminated equipment entered the cabin. The smell itself did not mean the moon possessed an atmosphere. Freshly exposed particles may have reacted with moisture and oxygen inside the pressurized spacecraft, producing sensations that could not occur on the airless surface. These observations confirm acute irritation. They do not establish the precise long-term respiratory effects of repeated lunar dust exposure. No human population has lived in a lunar habitat for months or years. Researchers can study Apollo samples, simulants, cultured cells, and animal models. But those methods cannot reproduce every property of freshly activated lunar dust inside a functioning base. The risk must therefore be managed before the complete medical outcome is known. A long-duration outpost needs a dust mitigation architecture, not a single cleaning brush. One approach is the suit port. Instead of carrying an entire spacesuit into the habitat, an astronaut enters through a rear hatch connected directly to the pressure vessel. Most of the dusty exterior remains outside. This reduces contamination, although the interface must maintain pressure, tolerate misalignment, and function after repeated exposure to regolith. A conventional airlock can use multiple zones. The outer section receives contaminated equipment. Cleaning occurs before the crew enters a cleaner intermediate area. Pressure and airflow can be managed so particles do not spread throughout the habitat. Specialized brushes and vacuum systems may remove loose material, but ordinary terrestrial vacuums cannot simply be transferred to the moon. Equipment must operate in vacuum, control electrostatic particles, prevent filter clogging, and avoid exhausting contaminants into sensitive mechanisms. Low adhesion coatings can reduce the force-binding dust to a surface. Another method uses electricity. NASA's electrodynamic dust shield places patterned electrodes beneath or across a protected surface. Carefully sequenced electric fields create traveling forces that move charged particles away. The system does not need to scrape the surface mechanically. It can transport dust from solar panels, windows, radiators, or other exposed equipment. In 2025, the technology was demonstrated on the lunar surface during Firefly Aerospace's Blue Ghost Mission 1. That result did not solve every dust problem, but it proved that active electrical dust removal could operate in the real lunar environment. Dust is only one half of the surface assault. The other is temperature. A complete lunar day, measured from one sunrise to the next, lasts about 29.5 Earth days. At many locations, daylight lasts roughly 2 weeks, followed by a similar period of darkness. Without sunlight, solar generation stops, temperatures fall, batteries lose performance, electronics require heaters, lubricants can thicken, degrade, or evaporate in vacuum. Materials contract at different rates, When sunlight returns, those materials expand again. Repeated thermal cycling creates fatigue in joints, cables, solder connections, seals, and structural interfaces. A component may survive one cycle, but accumulate microscopic damage across dozens. The South Polar region can reduce part of this problem, because the Moon's rotational axis has only a small tilt. Some elevated polar terrain receives sunlight for long periods, but there are no guaranteed peaks of eternal light. Crater walls, local topography, seasonal geometry, and the low solar angles still create darkness, and the deepest shadows the places most difficult to power. Heat and enter preserve something sunlight has erased from much of the Moon: ancient water, locked at temperatures that can fall below those found on the surface of Pluto. Near the lunar South Pole, some crater floors have not seen direct sunlight for billions of years. The sun remains close to the horizon. Elevated crater rims block its light. Deep below, the ground stays in permanent shadow. Temperatures in some of these regions fall below -200 degrees Celsius. The coldest measured areas can descend far lower. At those temperatures, a water molecule that reaches the surface may remain trapped across geological time. These places are called permanently shadowed regions. They exist because the Moon's rotational axis is tilted only slightly relative to the plane of its orbit around the Sun. On Earth, a much larger axial tilt creates strong seasonal changes in solar elevation. At the lunar poles, sunlight arrives at an extremely shallow angle. A small rise can remain illuminated for long periods. A deep crater only a short distance away may receive no direct sunlight at all. Its floor becomes a cold trap. A volatile molecule moving across the Moon can enter that shadow, strike the surface, and lose enough energy to remain there. If the temperature is sufficiently low, the rate at which it escapes becomes extraordinarily small. Over billions of years, even a slow delivery process can create a meaningful deposit. The water may have more than one source. Comets and water-bearing asteroids have struck the Moon throughout its history. Some of their volatile material would have escaped immediately into space. Some may have migrated across the surface before reaching polar cold traps. The solar wind provides another pathway. It continuously carries protons from the Sun. When these protons interact with oxygen bound inside lunar minerals, chemical reactions can produce hydroxyl groups and, under some conditions, water molecules. Impacts and temperature changes may release part of that material. Because the Moon has only an extremely thin exosphere, released molecules do not move through dense air. They follow ballistic trajectories, rising above the surface and falling back elsewhere. A molecule may make many such hops. If it lands in sunlight, it can be released again. If it reaches a sufficiently cold, permanently shadowed crater, it may remain. The evidence for polar water emerged gradually. In the 1990s, NASA's Lunar Prospector spacecraft mapped neutron emissions from the lunar surface. Scientists detected reductions in epithermal neutrons near the poles. The pattern was consistent with elevated hydrogen abundance. The spacecraft did not photograph blocks of ice. It detected the nuclear signature of a material capable of slowing neutrons. The mechanism begins with galactic cosmic rays. High-energy particles strike atomic nuclei in the regolith and trigger nuclear interactions. These collisions release neutrons with a range of energies. As the neutrons travel through the ground, they collide with other nuclei. Their energy changes according to the mass and properties of the material they encounter. Hydrogen is unusually effective at slowing neutrons because a hydrogen nucleus has nearly the same mass as a neutron. During a collision between similar masses, a large fraction of the neutron's energy can be transferred. Regions containing more hydrogen therefore allow fewer epithermal neutrons to escape into space. A neutron spectrometer above the Moon can map those deficits. But hydrogen is not automatically proof of clean water ice. It may exist in water molecules, hydroxyl compounds, solar wind implanted material, hydrated minerals, or mixtures distributed through regolith. Neutron spectroscopy identifies hydrogen enrichment. Other observations are needed to determine its chemical form and physical distribution. A more direct test came in 2009, NASA's Lunar Crater Observation and Sensing Satellite, known as LCROSS, deliberately sent its spent Centaur rocket stage into Cabeus, a permanently shadowed crater near the South Pole. The impact excavated material that had been hidden beneath the surface. LCROSS flew through the resulting plume, while telescopes observed from Earth and orbit. Spectrometers analyzed how the plume absorbed and emitted light. Water was detected. The plume also contained other volatile compounds, revealing that the cold trap had accumulated a chemically diverse inventory rather than pure ice alone. NASA's Lunar Reconnaissance Orbiter added another layer of evidence. LRO mapped polar temperatures, topography, illumination, neutron signatures, ultraviolet reflectance, and radar-related properties. These datasets allowed researchers to identify where stable ice could exist and where hydrogen-rich material might be concentrated. An analysis published in 2024, using LRO data, indicated that ice-related deposits may extend across a broader range of permanently shadowed regions than earlier assessments had established. That does not mean the South Pole contains easily accessible underground lakes. The actual physical structure remains one of the most important unanswered questions. The ice may coat individual grains. It may fill pore spaces in regolith. It may exist as small buried patches, thin lenses, or highly diluted mixtures. Its concentration may change sharply across only a few meters. Depth matters. A deposit close to the surface may be easier to reach, but more vulnerable to disturbance or loss. A deeper deposit may be better preserved, but require heavier excavation equipment. Before a base can depend on lunar water, robotic and human missions must measure concentration, grain structure, depth, mechanical strength, contamination, and thermal behavior directly. Extraction in a permanently shadowed region would be exceptionally difficult. Machinery must operate at cryogenic temperatures, cables become stiff, lubricants behave differently, batteries lose capacity. Electronics require heat, yet added heat can alter or release the very volatiles being measured. Excavation equipment would dig or collect icy regolith. The material would then be transported to a processing chamber. Heating would cause water and other volatiles to leave the grains as vapor. That vapor must be captured before it escapes. The system would separate water from carbon dioxide, sulfur compounds, hydrocarbons, and other substances. Purification hardware would then produce water suitable for technical or biological use. Electrolysis could divide purified water into oxygen and hydrogen. Oxygen could support breathing or serve as an oxidizer. Hydrogen and oxygen could potentially become rocket propellant, but producing them is only part of the challenge. Both must be cooled, stored, and protected from boil-off. Hydrogen is especially difficult to contain because its molecules are small and its liquid state requires extremely low temperatures. The entire chain must consume less energy and equipment than the resource is worth. Lunar water offers 4 major benefits. It can support human life. It can produce oxygen. It can add radiation shielding around habitats. And it could eventually provide propellant for surface vehicles or spacecraft. Yet water is not the moon's only value. Regolith contains atoms implanted by the solar wind over immense periods. Ancient surfaces preserve records of changes in the sun. Impact melts and crater ejecta help scientists reconstruct the bombardment history of the Earth-Moon system. Crater chronology links the number of impacts on a surface to its likely age. Lunar samples with known geological context help calibrate that method, which is then applied to Mars, Mercury, and other rocky worlds. Polar samples could reveal when volatiles arrived, where they came from, and how they migrated. The water is real at the regional level. A sustainable mining system is not yet real. That difference matters. The moon may contain material capable of supporting human life. But before extracting even 1 dependable kilogram of water, Artemis must complete a chain of operations that no crewed mission has ever performed together. Apollo 11 needed one Saturn V to begin its journey. Artemis depends on a launch vehicle, the Orion spacecraft, a lunar lander, new spacesuits, orbital docking systems, ground infrastructure, navigation networks, and a sequence of cryogenic propellant transfers. If one critical link is not ready, the mission does not leave on schedule. That complexity became even clearer when NASA revised the Artemis architecture in 2026. Under the updated plan, Artemis 3 is expected to become a crewed demonstration mission in low Earth orbit in 2027. Instead of immediately attempting a landing, the mission is intended to test critical systems closer to Earth. Artemis 4 is now aimed at returning astronauts to the lunar surface in 2028. 4 crew members would travel toward the Moon. 2 would descend near the South Pole and spend approximately 1 week conducting surface operations. NASA has also stated an intention to move toward roughly 1 lunar mission per year afterward. That is a program objective. It is not a guaranteed flight rate. Future dates depend on hardware performance, budgets, contractor progress, test results, regulatory approvals, and the ability to manufacture vehicles repeatedly. The decision to insert another demonstration mission may appear cautious. In human spaceflight, caution can be the difference between discovering a defect during a test and discovering it after the crew is beyond rescue. Engineers use several related processes to reduce that risk. Verification asks whether a system meets its documented requirements. If a docking mechanism must tolerate a specific structural load, verification uses analysis and testing to confirm that it can. If a life support component must remove carbon dioxide at a defined rate, verification measures that performance. Validation asks a different question. Even if every written requirement is satisfied, does the complete system accomplish the actual mission safely? A component may pass laboratory testing and still create an operational problem. A control may be difficult to reach while wearing gloves. A display may present information in a way that increases crew workload. 2 individually correct systems may exchange data incorrectly. Integrated testing is designed to expose failures at those boundaries. This matters because Artemis is not one spacecraft. The Space Launch System begins the crewed journey. Its core stage and solid rocket boosters accelerate Orion into space. An upper stage then provides the energy needed to send the spacecraft away from Earth. This maneuver is called translunar injection. The burn changes Orion's velocity so that its path extends outward and intersects the Moon's future position. The spacecraft is not aimed at where the Moon appears during launch. Guidance must target where the Moon will be when Orion arrives several days later. Orion provides a pressurized environment for the crew. Its guidance, navigation, and control systems determine position, orientation, and trajectory. Its propulsion system performs corrections. Its thermal control hardware removes heat produced by people and electronics. Orion must also bring the crew home. The human landing system performs another job. It moves astronauts between lunar orbit and the surface, then returns them to an orbital meeting point. That separation of roles creates interfaces. The vehicles must rendezvous. Their docking systems must align mechanically. Electrical connections must transfer power or data where required. Pressure seals must allow astronauts to move between spacecraft without losing atmosphere. Life support systems must accommodate the temporary movement of crew members from one vehicle to another. Even the spacesuit is part of this chain. An extravehicular mobility unit is not simply clothing. It is a personal spacecraft built around a human body. Its pressure garment prevents the astronaut's body fluids from being exposed to vacuum. The oxygen loop supplies breathable gas and carries carbon dioxide away from the helmet. Scrubbing hardware removes that carbon dioxide before it reaches dangerous concentrations. A liquid cooling garment transfers metabolic heat from the astronaut's skin. Pumps circulate water through small tubes. A thermal control system then rejects that heat. The suit must preserve mobility while maintaining pressure. Bearings, fabric joints, Gloves, seals, visors, communications, displays, and life support must all survive dust and repeated use. A suit that works perfectly in a clean laboratory may behave differently after abrasive regolith enters a joint. The planned lunar version of SpaceX's Starship adds another scale of complexity. Starship HLS is approximately 50 meters tall, roughly the height of a 15-story building. Its size offers an enormous potential increase in cargo volume compared with the Apollo lunar module. It could carry scientific instruments, surface equipment, supplies, and larger payloads that would be impossible to fit inside Apollo's compact lander. That size also creates operational challenges. The crew cabin is high above the surface. Astronauts and cargo require an elevator to travel between the vehicle and the ground. The elevator must function in vacuum, low gravity, extreme temperature changes, and lunar dust. Its cables, motors, brakes, power systems, and controls become mission-critical equipment. The lander must also arrive with enough propellant. Starship HLS is expected to depend on propellant transfer in Earth orbit. Tanker versions of Starship would deliver liquid oxygen and liquid methane before the lunar vehicle begins its journey. The final number of tanker flights cannot be treated as fixed until vehicle performance, transfer efficiency, storage duration, and operational configuration are confirmed. Whatever the number, the underlying physics is demanding. Liquid oxygen and liquid methane must remain at cryogenic temperatures. Even a well-insulated tank absorbs some heat from sunlight, Earth, nearby hardware, and the vehicle itself. That heat causes part of the liquid to vaporize. The process is called boil-off. As vapor accumulates, tank pressure rises. The vehicle must manage that pressure without losing an unacceptable quantity of propellant. Microgravity creates another problem. On Earth, gravity pulls liquid to the bottom of a tank. In orbit, the liquid may float, spread across surfaces, or form large moving masses. Gas and liquid may occupy unpredictable positions. Before transfer begins, the system must establish ullage control. Small accelerations, thrusters, internal devices, or other methods position the liquid so that pumps and outlets receive propellant rather than vapor. Two massive spacecraft must then dock. Fluid couplings must seal. Lines must be conditioned to cryogenic temperature. Pressure must be controlled to prevent violent flashing, excessive boil-off, or unstable flow. The transfer must be repeated with extremely low leakage. Each individual step is considered technically achievable. The challenge is demonstrating the complete sequence at operational scale and with the reliability required before astronauts depend on it. The journey ends with another violent process. A spacecraft returning from lunar distance enters Earth's atmosphere with substantially more energy than one descending from low Earth orbit. Orion's heat shield must protect the capsule as atmospheric compression and shock heating create extreme temperatures. Its ablative material is designed to decompose and erode in a controlled way. Instead of trying to remain unchanged, the heat shield sacrifices part of itself. Hot material and chemical products carry energy away from the capsule, while an insulating layer protects the structure beneath. The behavior must remain predictable across the entire shield. A small region eroding differently can create unexpected heating or structural stress. Artemis has not taken longer because engineers forgot how to fly to the moon. It has taken longer because multiple new systems must be tested, integrated, qualified, and human-rated before lives can depend on them. But even a perfect landing would not create a lunar base. If every mission must carry everything again from Earth, Artemis would become little more than a larger and more expensive version of Apollo. The first lunar base may not fail because it lacks a place for the crew to sleep. It may fail because a connector does not fit. A filter has no replacement, or a cargo flight arrives after essential reserves have already been consumed. A habitat is only the visible center of a much larger system. The system that keeps it alive is logistics. Human lunar operations can be divided into 3 broad levels. The first is a sortie. A crew arrives with nearly everything required for a short visit. It completes specific tasks, collects samples, and leaves before consumables or equipment life become limiting. Apollo followed this model. The second level is an extended duration mission. The crew remains for longer periods. Life support becomes more regenerative. Surface transportation covers greater distances. Maintenance and medical planning become more important. But the mission may still depend heavily on supplies carried specifically for that crew. The third level is sustained lunar presence. This does not necessarily mean astronauts must occupy the moon continuously from the beginning. Persistence is not the same as permanence. A persistent architecture can survive between visits. Its power systems continue functioning. Communications remain available. Equipment waits in a known condition. Supplies delivered by one mission support the next. Each crew inherits useful capability, rather than starting again from an empty surface. That requires pre-deployment. Robotic landers can deliver cargo before astronauts arrive. Power systems can be deployed and tested. Communication equipment can establish links with Earth. Rovers can inspect the landing area. Environmental sensors can measure temperature, radiation, illumination, and dust. A crew should not discover after landing that the power unit failed several weeks earlier. Critical hardware must report its condition. Controllers on Earth need enough telemetry to determine whether the site is ready to support human life. Pre-deployment also changes emergency planning. If supplies, a rover, communication equipment, and a backup power source are already operating, the crew begins the mission with options. If everything arrives with the astronauts on one vehicle, one landing failure can remove the entire architecture at once. Logistics planners must manage launch cadence. A lunar base consumes resources continuously, but rockets depart at discrete intervals. Each launch has a production schedule. Weather constraints, orbital windows, ground processing requirements, and the possibility of delay. Cargo manifests must therefore look beyond the immediate mission. Food, water, oxygen reserves, scientific equipment, tools, batteries, filters, medical supplies, replacement seals, cables, and lubricants all compete for payload capacity. Inventory forecasting estimates when each item will be consumed or reach the end of its certified life. This is difficult because actual use rarely matches the plan exactly. A filter may clog faster in a dusty environment. A suit component may require replacement after fewer excursions than expected. A crew may consume more water during physically demanding work. Uncertainty requires margin. But every spare part adds mass. The base must distinguish between ordinary spares and critical spares. A failed camera may reduce scientific productivity. A failed carbon dioxide removal blower can threaten the crew. Maintenance intervals are equally important. Some components are replaced after operating for a set number of hours. Others are inspected for wear. Some remain installed until sensors detect deteriorating performance. A machine's mean time between failures describes how often failures may occur across a large operating history. It does not guarantee how long one specific unit will survive. A pump with a long expected service life can still fail during its first week. Maintainability may matter as much as theoretical reliability. A highly reliable pump is not useful if replacing it requires dismantling half the life support rack, disconnecting contaminated lines, or shutting down the only oxygen loop for many hours. Engineers must design access around gloved hands, limited tools, cramped spaces, and the possibility that the astronaut performing the repair is tired or under time pressure. Connectors should be difficult to attach incorrectly. Components should be replaceable as modular units. Diagnostic software should identify the failing section without forcing the crew to inspect every line manually. When the correct spare does not exist, crews may turn to cannibalization. A valve, controller, sensor, or power converter can be removed from equipment that is already unusable and installed in a more important system. This can save a mission. It also creates a future weakness. The donor equipment can no longer be restored without another part. A base can gradually consume its own redundancy until the next failure leaves no options. Power dominates the logistics problem. Solar arrays can produce electricity without imported fuel, but their output depends on illumination, orientation, dust accumulation, and the angle at which sunlight reaches the cells. Near the lunar poles, the sun remains low on the horizon. Small changes in terrain can create long shadows. A ridge may receive extended illumination while a nearby depression remains dark. Batteries can bridge short interruptions. Longer darkness demands much more storage mass. Batteries also degrade through charge cycles, temperature extremes, radiation, and calendar aging. A surface fission power system could provide steady electricity independent of sunlight. Fission releases energy when heavy atomic nuclei split. That heat can be converted into electrical power using dynamic conversion equipment. Unlike solar arrays, the system could continue through darkness and operate in shadowed regions. But nuclear power introduces its own engineering requirements. The reactor must be transported and deployed safely. It must remain subcritical before activation. Shielding and distance must protect the crew. Waste heat must be rejected through radiators in vacuum. Moving parts in the power conversion system must operate for years with minimal servicing. NASA's 2025 Moon to Mars architecture update added a robotic mobility system and a fission power system as elements supporting future lunar exploration. Their inclusion reflects an important shift. A base cannot depend on astronauts carrying every object by hand or on sunlight always reaching the same location. Surface mobility comes in several forms. An unpressurized rover allows astronauts to travel farther than they can walk, but the crew remains inside spacesuits. The rover's safe range is limited by suit consumables, radiation exposure, terrain, and the distance astronauts could survive if the vehicle failed. A pressurized rover functions more like a small mobile habitat. Astronauts can travel while breathing cabin air, remove helmets, and remain away from the main base for longer periods. It expands exploration range, but adds life support, pressure seals, thermal control, sleeping arrangements, and emergency redundancy. Navigation near the South Pole is unusually difficult. The low sun creates long shadows. Bright illuminated terrain can sit beside almost black depressions. Cameras may struggle with extreme contrast. Surface features can be difficult to judge because there is no atmospheric haze to provide distance cues. Earth may not remain visible from every location. Crater walls and ridges can block direct line-of-sight communication. Relay satellites can carry signals around obstructions. A cislunar navigation network could provide timing and positioning services, similar in function, not identical in architecture, to satellite navigation around Earth. Without reliable time and position data, rovers cannot safely coordinate long routes. Cargo landers cannot target infrastructure precisely, and emergency teams may not know exactly where assistance is required. The International Space Station has already revealed the central lesson. Long-term human presence is a continuous sequence of inspections, software updates, filter changes, repairs, replacements, workarounds, and resupply missions. Success does not mean nothing breaks. Everything eventually breaks. Success means a failure does not force the entire outpost to be abandoned. Every lunar system can be tested, repaired, and improved, but building that resilience requires more time than the term of any president who has ever occupied the White House. Rockets do not recognize political parties. Aluminum does not care who wins an election. A valve performs according to pressure, temperature, and material properties, not opinion polls. But budgets determine whether a spacecraft is completed before the people who designed it are scattered across the industry again. That conflict sits at the center of every long-term lunar program. A deep space vehicle built to carry humans cannot move directly from computer model to launch pad. It must pass through years of reviews, manufacturing, testing, modification, and certification. The process begins before complete hardware exists. During preliminary and critical design reviews, independent specialists examine whether the proposed system can meet its requirements. They evaluate structural margins, thermal behavior, power demand, software architecture, fault tolerance, manufacturing plans, and interfaces with other vehicles. Closing a review does not mean every uncertainty has disappeared. It means the design is mature enough to justify moving into the next stage. Physical testing then challenges the assumptions used in the design. Structural test articles are loaded until they experience forces expected during flight. Engineers may push them beyond ordinary operational conditions to demonstrate margin and identify how failure begins. Launch produces intense vibration, rocket engines, turbopumps, aerodynamic flow, stage separation, and mechanical systems create forces across a wide range of frequencies. If one of those frequencies aligns with a structure's natural resonance, motion can amplify instead of remaining controlled. Vibration qualification exposes components to those conditions. Acoustic testing creates another assault. A powerful launch vehicle generates sound pressure capable of shaking panels, damaging electronics, or loosening connections. Spacecraft are placed inside specialized facilities where enormous speakers reproduce portions of the launch environment. Thermal vacuum testing examines a different reality. In space, there is no surrounding air to carry heat away through convection. Equipment gains and loses energy mainly through radiation and conduction into connected structures. Surfaces exposed to sunlight may become hot, while shaded areas become extremely cold. A thermal vacuum chamber removes air and cycles hardware through these conditions. Software requires its own campaign. Flight computers must interpret sensor data, control engines, manage power, detect failures, guide navigation, and communicate with other systems. Verification checks whether every function behaves as required. But software can fail through timing errors, corrupted inputs, unexpected interactions, or conditions designers did not anticipate. Hardware-in-the-loop testing connects real flight computers to simulated spacecraft environments. Faults are deliberately injected. Sensors provide abnormal values. Communications are interrupted. The software must respond without creating a worse failure. Finally, integrated flight tests place multiple systems together under real operational conditions. This sequence cannot be compressed indefinitely. Testing takes time. Failure investigations take more time. Redesign, manufacturing, and retesting extend the schedule further. A mature lunar surface architecture could require decades of sequential development because later systems depend on lessons learned from earlier ones. Political institutions operate on a much shorter clock. An American president can serve no more than 2 elected terms. Every member of the House of Representatives faces election every 2 years. Senators serve 6-year terms. But Senate membership also changes in stages. Federal appropriations are generally decided annually. A program requiring 25 years of sustained investment may cross 3 or 4 presidential administrations and 6 or 7 congressional election cycles. It must survive recessions, wars, public health emergencies, accidents, changes in national security policy, and new technological priorities. Each administration inherits a program designed by people it did not appoint. Changing the goal creates visible political ownership. Continuing the existing plan may not. This tension has repeatedly damaged lunar initiatives. In 1989, President George H.W. Bush announced the Space Exploration Initiative. The vision included a return to the Moon and eventual human missions to Mars. NASA studies produced ambitious architectures with large projected costs and long timelines. The initiative failed to secure the durable congressional support required to continue. The Moon remained. The political coalition did not. In 2004, President George W. Bush announced the vision for space exploration. NASA established the Constellation program, including the Orion crew vehicle. Ares launch vehicles, and the Altair lunar lander. Constellation was intended to return astronauts to the Moon and create a path toward Mars. By 2010, the program faced delays, funding problems, and growing concern about whether its schedule and architecture were achievable. It was canceled. Not everything disappeared. Orion continued under a modified role. Elements of shuttle-era technology later contributed to the space launch system. But missions, contractors, budgets, and timelines changed. Each transition consumed time. The relationship between budget and schedule creates a dangerous feedback loop. When annual funding arrives below the level assumed in a development plan, manufacturing slows. Tests move later. Contractor teams must remain employed for longer than expected. Facilities continue consuming money even when hardware is not moving quickly through them. The program then pays years of fixed costs before reaching the same milestone. A longer schedule raises the total price. The higher price attracts criticism. Criticism makes future funding less certain. Uncertain funding slows the program again. This is schedule erosion. It is not explained by a single incompetent engineer or one careless politician. It emerges from the interaction between technical reality, annual budgets, contract structures, and shifting requirements. The Government Accountability Office has repeatedly highlighted these pressures within Artemis. Its assessments have described ambitious schedules, substantial technical work remaining, integration risks, and limitations in the visibility of complete mission costs. This does not mean Artemis cannot succeed. It means calendars announced before major demonstrations should not be confused with verified operational capability. The architecture now includes mechanisms intended to make cancellation more difficult. One is international interdependence. The European Space Agency provides the European Service Module for Orion. It supplies propulsion, electrical power, thermal management, water, oxygen, and other critical support during flight. Gateway involves contributions from multiple international partners. Canada is developing advanced robotic systems. Japan and Europe are contributing habitation and logistics capabilities. Japan is also involved in plans for a pressurized lunar rover. These partnerships distribute cost and expertise. They also raise the political cost of withdrawal. Canceling a domestic project is one decision. Abandoning hardware commitments made to major allies creates diplomatic consequences across a much wider relationship. Commercial milestone contracts offer another form of resilience. Instead of paying only for labor and incurred cost, NASA can tie portions of payment to demonstrated progress. Private companies may also invest their own capital when the underlying vehicle has uses beyond one government mission. This does not eliminate risk. A commercial partner can miss milestones, encounter technical failure, lose financing, or change strategy. But a broader industrial base can prevent one government program from owning every part of the capability. The International Space Station proves that democratic governments can sustain a complex space project across political generations. Human beings have lived aboard it continuously since November 2000. The station survived the Columbia disaster, the grounding and retirement of the space shuttle, dependence on Russian Soyuz transportation, the arrival of commercial crew vehicles, budget conflicts, and severe geopolitical tension. It survived because many nations contributed irreplaceable hardware. Thousands of researchers depended on it. Jobs and contracts extended across political districts. Crews produced visible activity year after year. Canceling it became more difficult than continuing it. Competition with China may provide Artemis with another source of political momentum. China has completed increasingly sophisticated robotic lunar missions and has announced the plans for a crewed lunar landing around 2030. That competition can help sustain attention and funding. It can also recreate Apollo's central weakness. If Artemis becomes only a race to place another flag near the South Pole, political urgency may disappear once the race is decided. Speed may replace sustainability. A single landing may be optimized at the expense of the infrastructure needed for the next one. The deeper question is whether Artemis will become another sprint or a system valuable enough that no future administration wants to dismantle it. Apollo achieved victory in a moment. Artemis will succeed only if its value survives after the moment of victory has been forgotten. When the next astronaut steps onto the moon, the world may call it a return. Television networks will interrupt their schedules. Images will move across every continent. Political leaders will describe the event as the beginning of a new age. But if no mission follows, that footprint will be only the 13th in a program that ended too soon. The landing itself is not the final test. The next landing is. The mystery of the missing half-century now has 3 answers. Apollo ended because it achieved the geopolitical purpose that had created it. The program was built to defeat the Soviet Union in a visible contest. Once that victory was secured, each additional mission produced less political value while continuing to demand extraordinary resources. The second answer is industrial. America did not lose the physics of lunar flight. It lost the ecosystem that turned the physics into working machines. Factories closed, tooling disappeared. Suppliers moved on, engineers retired. Tacit knowledge dissolved as the workforce dispersed. The blueprints survived. The production capability did not. The third answer explains why modern technology has not produced a rapid repeat of Apollo. Artemis is attempting to build an architecture Apollo never possessed. It must combine reusable or repeatedly manufactured transportation, longer surface stays, advanced spacesuits, regenerative life support, cryogenic fluid management, surface power, logistics, communications, mobility, dust control, and the foundations of local resource use. No known part of that objective requires a new law of physics. That statement should not be confused with readiness. A system can be physically possible and still be far from operational. Orbital refueling must be demonstrated at the required scale. Hardware must survive lunar dust and temperature cycling. Life support equipment must operate for longer periods with limited maintenance. Surface power must remain reliable through darkness and extreme cold. The components must be integrated. They must be qualified. Then they must prove that they can keep working outside a laboratory, where a failed connector cannot be replaced by a technician standing in the next room. The reward for solving those problems reaches far beyond another flag. The lunar South Pole offers scientific material that the Apollo crews never touched. Polar samples could reveal how water and other volatile compounds arrived, migrated, and became trapped. Their isotopic composition may help distinguish contributions from asteroids, comets, solar wind chemistry, and processes within the moon itself. Context will matter as much as composition. A sample collected from a known depth and geological layer carries more information than a fragment with no documented origin. Temperature, illumination history, grain structure, and surrounding mineralogy can help scientists reconstruct how the deposit formed. Regolith also preserves implanted particles from the solar wind. The upper surface is continually exposed to protons, helium nuclei, and trace ions flowing from the sun. Some become embedded in mineral grains. Buried layers may preserve records from different periods. Reading that record is difficult because impact gardening mixes the surface. But carefully selected cores could help researchers investigate changes in the sun and the space environment across long timescales. Lunar rocks also calibrate crater chronology. On worlds where samples cannot be collected directly, scientists estimate surface age by counting impact craters. A surface with many craters is generally older than one with fewer. But crater counts require calibration. Apollo samples linked radiometric ages to specific geological terrains. Samples from new regions could improve the chronology used not only for the Moon, but also for Mars, Mercury, and other rocky bodies. A long-lived seismic network would add another layer of knowledge. Apollo seismometers detected moonquakes and impact events, revealing that the Moon is not completely inactive. Some shallow moonquakes can be relatively strong and may last longer than comparable events on Earth. Because dry, fractured lunar rock attenuates seismic energy differently, a modern network distributed across several locations could examine the crust, mantle, and core with far greater precision. It could also measure local hazards before large habitats are built. Then there is partial gravity. The human body has never been studied for months in 1/6 gravity. A lunar base could determine whether that level is sufficient to reduce bone loss, muscle atrophy, cardiovascular deconditioning, balance disruption, and fluid redistribution compared with microgravity. The results would matter for every future settlement concept beyond Earth. The technological value may be equally important. Closed-loop life support on the Moon would teach engineers how to recover resources while operating far from immediate resupply. Autonomous maintenance would allow equipment to detect degradation, isolate faults, and guide repairs before a small failure becomes catastrophic. Surface fission systems could demonstrate reliable power independent of sunlight. Cryogenic fluid management could support landers, fuel depots, scientific equipment, and missions deeper into space. Robots would learn to excavate, transport cargo, connect power systems, and inspect infrastructure in vacuum, extreme temperature, and abrasive dust. These technologies would not transfer perfectly to Mars. The Moon is not a miniature Mars. Mars has an atmosphere, a day lasting slightly more than 24 hours, different gravity, different soil chemistry, greater distance, and communication delays that can exceed 20 minutes one way. But the Moon offers a place to test deep space operations while remaining only several days from Earth. A failed lunar experiment may still be repairable by a future cargo flight. A medical emergency remains extremely serious, but the return journey is measured in days rather than months. That makes the Moon a proving ground not because it duplicates Mars, but because it exposes weaknesses before those weaknesses travel tens of millions of kilometers farther away. The economic claims must remain disciplined. Water ice does not automatically create a profitable lunar economy. A detected resource is not the same as a reserve that can be extracted usefully. Several questions must be answered by measurement. Is the ice concentrated enough to collect efficiently? Is it accessible beneath the surface? Can machinery operate for years in permanently shadowed terrain? How much energy is needed to excavate, heat, capture, purify, electrolyze, and store the product? Does producing water or propellant locally cost less than delivering an equivalent resource from Earth? Until those questions have operational answers, lunar mining remains a capability to test, not a guaranteed business. Progress will therefore look less dramatic than Apollo. It may begin with an electrodynamic shield removing dust from a radiator. A power system may survive its first extended darkness. A robotic vehicle may position supplies before the crew arrives. A water processing unit may operate through thousands of cycles without replacement. A habitat may wait empty for months, then power up for a second crew. That second use would matter enormously. It would mean the previous mission left more than footprints. It left capability. The next crew would arrive with better maps, stored equipment, functioning communications, tested emergency procedures, and knowledge purchased through real experience. They would not begin from zero. Apollo demonstrated courage under pressure. It showed what concentrated funding, engineering talent, and national urgency could accomplish before a deadline. Artemis must demonstrate a different virtue. It must sustain purpose when no single crisis forces everyone to agree. It must survive quiet years, budget arguments, failed tests, political transitions, and moments when progress is real but invisible to the public. A mature civilization does not merely accomplish the extraordinary. Once, it preserves the knowledge, infrastructure, and commitment required to do it again. Apollo was not the dawn of the lunar age. It was a flash of lightning at the height of the Cold War, bright enough to carry 12 people to another world, but too brief to build anything that could outlast them. Artemis will be slower, more complex, and more vulnerable to failure than its promotional images suggest. But if one habitat is used twice, if one power system survives the lunar darkness, and if the next crew continues where the previous crew stopped, humanity will achieve something Apollo was never designed to accomplish, not merely reaching the moon, but ending the cycle of reaching it and then disappearing.